All right. That should do it. I will begin with a word of prayer, although I don't always do that in these. Dear Father, we thank you for this day. I just pray that you guide our steps today, help us to understand the solution to the test and whatever else we have time for today, Lord. In your name I pray. Amen. Okay, so, this is problem one. I said, and so, I don't know, I originally had wording on this problem that said calculate directly from the definition, but then I didn't like the amount of space those words took up, so I converted it back to by direct calculation of the integral. And I thought that should be clear, but people were trying to apply Cauchy integral theorem or other weird stuff here, and there's just no need. Well, anyway, I will try to make the wording of the problem a little bit more unavoidable next time, and yet still the people who were anywhere close to being right did understand the wording to mean what it meant. So direct calculation, parameterize the curve, which is, here it is, and then work it out. So, z minus z naught to the n is r e to the I theta to the n, and then derivative of the parameterization just brings down an I e to the I theta. Now there's also an r, which I factored out front. And then at this point we split paths. Either we have n equal to minus 1, which is a nice special case. N equal to minus 1, this just becomes 1. So this whole thing integrates to 2 pi, and you got 2 pi I r to the minus 1 plus 1, otherwise known as 2 pi I. If n is not equal, n plus 1 is not equal to 0, in other words, if n is not equal to minus 1, then we can integrate this because, the derivative of e to the lambda. Well, anyway, this is, you can differentiate that, get back that. See, because when we differentiate, chain rule pulls down an n plus 1 times I. So I had people doing various, some people kind of had this right, and then did kind of like a power rule here, which was interesting. I won't name names. It's okay? Okay. Whoever, all the students here, I'm not sure which one I'm talking about, but all right, so anyway, that works out to 0. The other people expand it in terms of sine and cosine. They're like, well, if you integrate sine or cosine over an integer multiple of 2 pi multiple full cycle, it goes to 0. That's also great. Fine. But anyway, in summary, we have that. Now, if we had the Cauchy residue theorem, this problem becomes almost a tautology. See, because if you have, if you look at z minus z naught to the n, right, then the residue is 0 unless n equals to minus 1, in which case the residue is 2 pi I. So this makes complete sense if you think about Cauchy residue theorem. Also, if n is not equal to minus 1, and I had one person kind of do this, and I was actually kind of happy about this. This is on the verge of direct calculation. Not quite, but kind of. I could kind of see why a person would think this was direct calculation. If n is not equal to minus 1, you know what else we could do here? We could say, well, f of z is equal to 1 over n plus 1, z minus z naught to the n plus 1, right? And you can easily calculate that df dz is z minus z naught to the n, yeah? So the integral of, z minus z naught to the n dz over a circle, right? It would be, pick 2 points on the circle, I suppose, at the same point, right? And so you'd have f of p minus f of p, which of course would be 0. And that'll work swimmingly well as long as, and there you go. There is an antiderivative for this function, provided n is not equal to minus 1 all the way around. So, which is interesting, right? Because when n is less than minus 1, right? When n is minus 2, minus 3, minus 4, whatever, there's check that out. There's an antiderivative all the way around the origin, and yet there's still a pole in the middle. as a student, I struggled with the idea that the simple pole, like the pole of order 1, behaves differently than like the pole of order 2 or order 3. You know, it's funny. So then problem 2 was meant to be a friendly problem. And a couple of you, maybe 3, just did it as I was hoping, which was to use the Weierstrass M test compared to the p equals 2 series, which is pi squared over 6 by calculus 2 or 3, depending on who we ask. Hey, I'll make them work that out in differential equations so you can see it. Sound good?
Wait, so I can see it?
Yeah, I'll make them show it to you. I'll say work this out and show Bethany. All right? Okay. That'll be like part of the homework problem. Like find Bethany and show her.
Sounds good.
If your last name starts with letters T or P, and I have likened you to a Muppet.
Wait, T. Who's in that class? I know Taylor.
Wait a minute. Oh, her last name isn't. Her first name's Taylor, isn't it?
Yeah.
Dang it.
Last
R. What's it?
Grace.
Yeah.
Or Katie's in that class.
I was trying to P is the last name of the other one, right? Mm-hmm. Anyway, I'll find an odd way of saying it that will limit the talking to you to just them. But yeah, we can actually prove this with Fourier expansion. If you look at the expansion of x squared and look at the Fourier expansion of that, you can prove that. It's a relatively simple calculation. Anyway, so that's a majorant because it bounds this, and so that converges uniformly because that's one of the things we get from the Weierstrass M test. Now, somebody else used the ratio test here, which I think might work out okay, and that was okay, but if you were to use the ratio test, you should probably also claim that it gives you uniform convergence, because that's not something I emphasized in here, and it should be said if you're going to use the ratio test. But anyway. Now, problem 3 was meant to be a gift. It's a gift that some of you freely took, and others of you not. Well, I mean, I think about 7. Wait a minute, I forgot how many people took that. Okay, so there's only 7 or 8 of us left in the class. All right, so 4 or 5 of you, I think, did this well. So, I don't know. And I feel like this is actually something we should ask Calc 2 students anyway. I know sometimes we shy away from actually asking the proof tests, but maybe we ought not. Problem 4. So problem 4 to me is kind of a bellwether that you guys are not quite done thinking about this stuff. Because if people had really gotten through, had conceptualized chapter 11, this should have not been like hard at all. And so the fact that people are having trouble with this problem suggests to me that whatever grade you made on this test, you're going to replace it with a better grade on the final, because I think that people can do this question on the final if it reappears, because it's not hard. We just have to, use what we're given. So we got 0 of order 3, 0 of order 5, which means by our go-to theorem that there exists, analytic non-zero at the center point factors, cofactors, whatever you want to call this thing. And so then I just look at the quotient and regroup stuff and look at it. I got a pole of order 2. So, oh, you like this one? Yeah. And the next one, yes. The next one was also meant to be friendly. This is a straight up Cauchy integral formula problem, right? Although, how would we do this now? That's right, we would now use the residue. And what residue would we use? Yeah, I'm not sure rule 1, 2, 3, or 4 helps us here, does it? Not sure. Huh. Eh. Yeah. I think this is actually yet another residue rule that we haven't. I mean, you can look at this as yet another residue rule. Let me try to write it down. So this is this is a residue rule for a. This is a pole of order 3, I think. Well, no. Goodness. Where would I want to calculate the residue at? At I, right? That is kind of what I'm doing. So why would that make sense in terms of, yeah?
Because you end up with Cauchy cinch of 1 now.
Well, yeah, that's because z squared, when you plug in the -1, it becomes, plug in I into z squared, we get minus I squared, which is -1, but then I use the even and oddness of Cauchy and cinch to pull minuses out as to confuse students. This is my goal. But the question is, okay, so I think I understand how to explain this in terms of residue. So, we're looking at 1 over z minus I. Again, for this test, you guys didn't know about residue, so you're just supposed to think Cauchy's integral formula. And, but if you think about this times the cosh of z squared, what are you trying to do? You're trying to rewrite this as, stuff, and then some number, right, divided by z minus I. I mean, you're after that, whatever that is. So if you look at that, you could look at this as z minus I cubed, and then, well, cosh of z, let's call this thing, let's call it g, right? If you think about cosh of z squared as being g of z, what is that? I mean, that's holomorphic at I, is it not? I mean, that's an entire function, so great. And then the thing is, we can do the Taylor expansion for that about I, right? That's going to be like g of I plus g prime of I times z minus I plus 1/2 g prime prime of I times z minus I squared. And you see from just multiplying the Taylor series by this reciprocal term out front, right, that this is going to be the residue of, cosh of z squared over z minus I cubed at I. But that's exactly what I calculated. I mean, that's what that's also what the Cauchy's generalized integral formula said, right? It said take the second derivative of the numerator function, differentiate it 2 times, plug in I, multiply by 2 pi, I over 2 factorial, right? But I don't know, isn't it clarifying to think about it? We're just calculating the residue of the integrand as opposed to applying, because the generalized Cauchy integral formula is not, it's not that it doesn't solve the same problems, it's just it kind of is a little bit indirect, the calculation, right? The residue calculation, I think, to me it's more direct, I don't know. But anyway, there's the solution to that. And actually, a couple of you guys got that one. Pretty happy about that. I think 2 people got this wrong because they couldn't differentiate hyperbolic cosine of z squared. There is a chain rule. Very proud of problem 6. So, we do long division, and out pops the polynomial piece and then the proper rational function. So the principal part is the polynomial piece, and since it's first order, that makes it a simple pole at infinity. And yes, it's meromorphic. In fact, the rational functions are the only meromorphic functions on the extended complex plane, as we proved, quote unquote proved. I sketched a proof of that in class, at least. I mean, maybe saying I proved it is a little bit much, but your generation doesn't appreciate it. But I would point out that if you look at this carefully, you can see 8, 6, 7, 5, 3, 0, 9. You had to use your imagination for the O.
I didn't do long division.
Oh.
No, I still got it, but I just added things and factored out. And
You know, more power to you. Long division is just an algorithm. You know, it's not somehow more correct than algebra. This problem I invented for you guys. So the idea of this problem came to me because I wanted you guys to try to explain to me, man, that is annoying. I wanted you guys to, if I do this, does it help? No, it's just, yeah, it's that moving. I need like a stabilizing pokey stick or something. Should go back and give a lecture under the projector. So if you pause this while you're watching it, anyway, we'll post this, of course. The idea is simply this: if we have a simple 0 at z1 and that's the closest simple 0, then 1 over f is holomorphic out to z1. If it's holomorphic, it's analytic. So it must converge to that series, which is given because the series is uniquely defined by the center.
Can you tell me what's wrong with the
Now, let's see here. So, of course, I don't know. I'm not entirely convinced.
I'm not completely sure what it's asking.
See, what I'm looking for is the statement that it's clear that the function's holomorphic, which implies analytic.
So like it's asking.
In some sense, you're assuming what I want you to prove here, I think. And maybe it's not entirely clear, you know. You said that the zeros are isolated. Okay. Okay, I understand. Yeah, I give you back a couple more points.
I'm just wondering.
No, I see what you're saying. So you're saying that since the zeros are isolated, well, isn't that what I'm telling you though? Is that the zero is isolated? That z stop it. That z1 is the closest zero to z naught. So f of z is non-zero for that disk. So what I was trying to get at, I mean, I don't know, maybe my wording needs to. I'm struggling to find wording which was more guiding to you guys, but not just giving it away. And I'm not sure I did the best job on that. But what I'm trying to get at was, so you have f of z1 is equal to 0, but of course anywhere in here we have f of z not equal to 0. And so then 1 over f of z, if we differentiate it, has a well-defined derivative, right? It's minus 1 over f squared f prime. And I don't know what that is exactly, but I do know that it exists, and right? So that function's holomorphic, but then we know that holomorphic implies analytic. So, I mean, I have used this. We had a theorem at some point which said that the closest zero, I mean the closest pole, like I think we had a theorem that if you have, well, this is the thing, is do we have that theorem? Curses. A theorem. Yeah, holomorphic implies analytic, definitely we had. What I'm thinking about is if you have a power series, how do you figure out the domain, yeah, the radius or the disk of, the radius of convergence? And so what I'm trying to get at here is, if you know that there's a divergence for the function which it's modeling, like 1 over fz is the series. The series, this series, is defined by the reciprocal function, right? So what I wanted you to do is tell me something about why that reciprocal function is holomorphic where it is. Therefore, it must be analytic just the same, but there's a unique power series representation for an analytic function because you can calculate it by the derivatives of the function at the center of the disk of the convergence. And so that's why I was arguing uniqueness here. This is what I was trying to fish for, apparently badly, but.
I have a number.
A number? You playing the numbers again, huh?
Yeah.
You've been hanging around that other professor I won't name. Oh, you want me to, yeah.
Well, I have the number if you want to check the number when you're given the number.
Ah.
I have the actual number.
Oh, I gotcha.
So
Oh, yes. I would appreciate you. Yes, thank you. Sorry. We are actually talking about something. This is not some kind of like cryptic liberty joke or something. Usually I'd assume it's some kind of joke, but I mean, it may be a joke. Remains to be seen. Okay, so the larger point here was B is just the application of A. See, because this is a function which has a 0 at plus or minus pi I over 3. And so, the expansion of sinh 1 over the reciprocal of sinh 3z is going to be analytic right up to the singularity. And then the question is, how far is that singularity from 1?
This one I wasn't that far off on. I just had an N instead of an I.
Ah. Yeah, anyway, talk to me after. I do think I owe you a couple points on this one. I just, I got pinched for time between class and other things. I couldn't see when I was looking at it the first time what yeah. And I understand you're not even asking for points. It's just, it bothers me when I realize that maybe I should have gotten a point or two more. Because I am reminded of myself and my experience of not getting the points back when I was clearly owed them, and it still bothers me some 20 years later. But anyway, it shouldn't. I mean, it's just the learning is what's important, right? In principle. Now this one, nobody got. And maybe that's understandable. I mean, I gave you guys this Herculeanly difficult problem that involves the same mathematics, right? But it would be easy to not have, well, maybe one person got this, but a different way. So the idea was just that because we have a quadratic, we can bound it by a bound. Well, this one we can specifically work out like this. I think this is okay. So, to make the denominator smaller makes the fraction larger, right? So I use the reverse triangle inequality that whatever you want to call this thing. Oh, you're fine. I'm just trying to think about if I need to speed up. So does that first step make sense to you? Yeah. Okay. And then I was like, well, then I thought about it. I'm like, well, if I make this as large as it can possibly be, then wouldn't that make this difference as small as it could possibly be, and hence the fraction largest? So in order for that to make sense, I need to be sure that this term is actually smaller than that term. But it's fairly clear that that's going to be the case if r is much, much larger than 1. and also b, c, and 2br, right? So like, as long as r squared is larger than all this stuff, significantly larger, then clearly that second piece is going to be dwarfed by the first piece. And so you just want to subtract away as much as you can to get the largest absolute value, was my thought. So then that gives me this, which is positive, so I dropped the absolute values and got that. So I got a quadratic in R with some coefficients, whatever they are, I don't care. ML theorem, 2 pi r over r squared minus that. And of course, as r goes to infinity, that goes to 0. So on the flip side of things, you know, I got 2 pi I alpha plus 2 pi I beta using the Cauchy's integral formula with m equal to 0 or 1. I forgot how we label m. But anyway, Cauchy's now, right, because anyway, so we Cauchy generalized integral formula, I got 2 pi I beta, which says that alpha is equal to minus beta. So, of course, you could recognize this now as what? Now it's just straight up Cauchy's residue theorem, right? Because if we integrate 1 over gz, which is alpha over z minus z1, plus beta over z minus z2, then there's singular points z1 and z2. And so Cauchy's residue theorem says any counterclockwise curve which encloses z1 and z2, just get me the sum of the residues times 2 pi I, which is that. So they gotta be equal and opposite. Which we saw today on a smaller scale in class for the z squared plus 1, 1. Same math. And then this one. All right, so here it is. Although I will say, I have to say, the way Sam is doing these is interesting. He's got a system. I think it's better than mine. So if you guys want to see a sneakier, cleaner way of doing it than I'm doing it, look at Sam's. But what I do is to recenter the world where I want it to be centered. And namely, I want to create a z minus 2i. So to achieve that goal, I add and subtract 2i judiciously, like so. But then I realize I'm in part A, where I have control over z minus 2i over 2 being less than 1. I need to make that my what's the word? Ratio. So I factor out the 2i, and I'm off to the races, see, because that is an allowable radius, or rather ratio for the geometric series. Put in my minus, doesn't really matter, of course, except that it does in the formulas. Not so much for the radius, though, right? Anyway, so I have, I do have that condition by star. And there you go. And then just cleaning it up, bringing the 2i together. And I mean, if you wanted to fuss about this, you could break it up into further cases, right? Because like I to various powers, it's got that fourplicity. It's like plus 1, minus 1, plus I, minus I. So if you wanted to, you could kind of like further separate terms here. But I thought this was a good answer for us, and we should just leave it like that. And let's see here. And then part B, I again add and subtract 2i, but this time I need to create something like that because I know that that has modulus less than 1. By star star, which was labeled up there. And so I get this, and then again, just collecting stuff back together gives me that. My scan didn't pick it up very well. I had shaded part A in red, and then I shaded part B in green, which just did not show up in the scan at all. Worthless. That's annoying. And so my point was like, all of this is the green, and all of that's the red. Like you can see, there's these two cases. And neither of these Laurent expansions would be of any use to us if we were calculating something with the residue theorem for this function, because it has a pole at 0. Yeah. No, you can calculate, I mean, Well, what I'm trying to get at is what is the, if I were, suppose I was trying to, what's the residue theorem say is my question, yeah? So what's Cauchy residue theorem say? It says be a bounded domain, suppose, except isolated singularities, right? These are supposed to be singularities. We take the 2 pi I times the sum of the residues at the singularities. Well, the problem we were just looking at, I is not a singularity of 1 over z. So, it wouldn't help us calculate an integral of that function. I mean, that calculation is primarily just to confuse students and take away their points. It worked. Mission accomplished. I was not trying to be mean. Oh well. Now, FTC2. So there's like a variety of different ways to prove FTC2. I like this way. So if it has antiderivative big F in the complex sense, then that means that F is complex differentiable, which means that partial df dz is partial f partial x, but it's also minus I partial f partial y. So I can convert my f to partial f partial x, or I can convert it to minus I partial f partial y, which then gives me this, which is df, and then by our earlier work on the, if we have an integral of a total differential, then it's the difference of the level of the function being totally differentiated at the endpoints. Or I have a proof over here of a very complicated real notation version of the same thing, which ultimately gets down to like the differential of A and the differential of B. Here I've invented A and B for the real and imaginary components of the primitive big F or little f, whatever. It doesn't matter if you like what I read to start with, you can ignore what's over here. And then this, I mean, I would have gone with this if I were you guys. A lot of you did, because that's, I don't know, of all the different proofs we've stumbled upon in this course, this is one of the most beautiful and simple ones. Just this understanding that a holomorphic function by Green's theorem has to integrate to 0 around the edge. It's really, really neat. I like this. This is one of the things I saw. I remember when I first took complex variables, just seeing that and just thinking, this is really neat and simple. And then this, you can see the notes. Okay, no need to belabor that again. Pretty much everyone in here, almost without exception, anticipated me asking one or the other of these and was prepared. So anyway, that's it. Any other questions? No? All right, yeah. Wait a minute, why did I shut that? Idiot. So I guess that's it for today on the complex side of things.